This is the second physical science video lecture on graphing techniques. We're going to start with the experiment. So in the experiment, there are a few things that we're going to need to identify before we start graphing. The first of those are what variables are we using? And a variable, as I know you're all familiar with, something that changes during or as part of the experiment. There are two types of variables that we're concerned with. The first is an independent variable, which is something that we change directly. Think of the word independent. It's out there on its own. This is not something that's changing because of the experiment. It's something that we're testing. So think of it that way. It can be called manipulated variable because we're manipulating it. It's the one that we have control of. We want to learn more about what does this do in our situation. The other type of variable is a dependent variable, and this is one that depends on what's happening in the rest of the experiment. Something that changes because of the experiment and is also called a responding variable. Basically, a dependent variable is something that we measure. So in the case of our rockets that we're running, most of us have chosen as a classroom experiment to change how much water is in one of the bottles. That would be our independent variable, something that we control. And we're going to measure then what effect that has on our flight distance, which is our dependent variable. But there were a lot of other things about the rocket, characteristics about the rocket, that we could have changed, but we decided not to. We wanted to hold all of those things the same so that we'd have a good, consistent experiment. Those things are called controls. Everything else that's held constant and doesn't change during the experiment. For our rockets, that would include things like wing size and shape and location, how many wings there are, what type of bottles we used, the angle that the launcher is set to, and air pressure, and all the other things that we listed. Well, once we decide all that, decide how we're going to do the experiment and perform it, we take some data, and then we get to the point where we want to analyze that data. And a really helpful tool for helping us analyze and visualize what the data is doing is a graph. It's not just a tool for math class that they make you learn. It's really, really helpful for a lot of stuff here as well. And we're going to go over some of the rules for graphing and how to set up a simple graph. You'll also get a document titled Rules for Graphing, which follows along with and summarizes this as well. The first thing we need to do is identify those dependent and independent variables, which we've already done as part of the experiment. The independent variable, which is the one that we control directly, will go along the x-axis. That's the bottom of our graph. And the dependent variable, which is the one that we're measuring, goes along the y-axis. We want to orient our paper so we can fit all of our data and draw axis lines. So sometimes this will be landscape, which is sort of the wide way. Sometimes it will be portrait, which is the tall way. And we want to use as much of that paper as possible. Certainly at least half of a sheet, and often all of the sheet, because when we draw it out and do some calculations on it, we'll get the most precise results from a larger graph. So the more of the paper we can use, the better. We need to scale and label the x-axis. What scale means is we need to be able to have room for all our data points. So let's say we went from 0 to 100. We need to get 0 to 100 on that scale. However, we can't just jam it all in there. We also have to have the same scale throughout. So let's say that we have data points at 2, 5, and 40. We can't put those next to each other. The distance between the 2 and the 5 is 3. Well, between the 5 and the 40 is much bigger than that. We need a much bigger gap. Let's say that we say each square in our graph paper is 5. Well, then that 5 would be, let's do the math, 7 squares away from the 40. We'd have to have a much bigger gap. The important thing, the thing that we'll practice in class, is keeping that scale the same. So instead of deciding I want this point, this point, this point, we say I'm going to start at 0, and each square will be going up by 5, for example, or 10, whatever the units we have. The label goes below that x-axis, and we just want to title it with whatever our independent variable is. In parentheses after that, we'll put the units so that anyone looking at our graph will know what we measured and what units we measured it in. Next step is to scale and label the y-axis. We'll use the same techniques as the x-axis, but this will be on that vertical line. Title our graph. Your title should not be something like "My Wicked Cool Rocket." It's got to describe what you're actually showing within the graph. Usually, this will be prominent and centered, and it'll usually include both variables' names, often written something like y variable versus x variable. When we're talking about our rockets, we might say something like flight distance of our rocket versus the amount of water in whichever bottle we were doing. Next step is to plot our data. I use dots here. Oops, let's get to line. Use dots here or open squares. The actual figure used doesn't matter as much as being consistent with it. And we'll have data that has our x coordinate and our y coordinate. So find one of them along the x, your independent variable. Let's say it's 5 meters. Go over to the 5-meter mark on your bottom plot, and then up to whatever the corresponding y value is. Once you've plotted all of your data, add a best line or curve. What a best fit line means is something that goes in through the center of the data, but not point to point. So if your data looks like it's basically in a line, use a ruler and draw this line through the middle of your data. If it's a curve, draw a smooth arc through the center of the data, and that'll usually be freehand. Do the best that you can. In neither of these cases should you ever put a point-to-point line or a curve. Having this smooth best fit line or curve tells us a lot more about the data than doing the point-to-point, because we have some inconsistencies in any experiment that we do. And drawing that smooth line sort of takes an average of those and levels them out. I know this is a lot at this point. Let's do an example together. So we've got an experiment performed to correlate the number of trips needed to make the bathroom, you needed to make to the bathroom, depending on the amount of soda you drank throughout the day. So let's identify a few things here, and then we'll set it up using a notebook file. We want the number of trips we needed to make to the bathroom, depending on the amount of soda you drank. Well, that kind of sets it up really well for us. The number of trips to the bathroom depends on the amount of soda we drank. So this amount of soda we drank is what we control. That's our independent variable. It will go on the bottom along the x-axis. The dependent variable will be the number of trips we needed to make to the bathroom. So let's take that over to the Smart Notebook, and we're going to draw a few lines just to do that. So we've got an x-axis here. We've got a y-axis here. And I want to just title those quickly. We don't have all the data to put in here. I'll show you what a completed graph might look like. I want to title this with my my independent variable, which was amount of soda drunk. Now, this being science class, we'd probably measure that in either milliliters or liters. Let's assume you drank a lot. Over on the y-axis, we're going to put our dependent variable, which is the number of trips to the bathroom. Since this is just a counted number, we don't need to actually put a unit after it. It's just the number. I'm going to rotate that so it matches up well. Scoot it over into place. Now the scale here is tough since we don't actually have, I don't have the data, and I probably should. Scale is tough. On a graph paper, we just make sure each of the lines in the graph paper was the same value, and each value going up was the same. We'd put a title across the top. This can change a little bit, certainly, from graph to graph. Since we're measuring number of trips to the bathroom, depending on the amount of soda drunk, I'd probably just put something to that effect. Number of bathroom trips versus amount of soda drunk. Tells us what our graph is showing, tells us what our experiment had. Now, I do have a plotted version of this, since we basically set it up right, including the data. So what that would look like, and I'll try and get the data up here in the next version of this. I plotted the data, and those are the dots here. Set up, same amount, same way that we set it up in the other, in the notebook file. The thing that's added here is called that best fit line. I can have the computer do it. We're going to start by graphing by hand because it gives you a much better feel for what a graph should look like and how to set it up. It's simply too quick and easy to set up a bad graph when doing it on a computer. So if you can grasp what you need to while doing it by hand, you'll make much better graphs when you switch over to a computer, which we will do during this year. This is called that best fit line. You'll notice that some data points are above and some are below our line because it's telling us the average number. We're going to practice this in class, but hopefully this is kind of a quick overview of what you need to know to produce a good graph.